It just picks the fastest. And then round 2 starts. And round 1, round 2 begins, and round 2 ends. So we assume in round 2 nothing happened, no change in receiving rates. But what you'll notice is that these costly pairs have remained. So in effect, the pair selection algorithm doesn't even take into consideration the fact that these pairs are costly. So how do we propose to fix this, to rectify that situation? Well, we propose to assign a certain credit, which is where the heuristic comes in, to costly pairs. And we're going to attempt to replace costly pairs with localized pairs that would give an equal download rate. Let's see, let's take this a step further. So we assign a credit to pair 2 because he...
Now, what do the color grades mean in this? Like, what does darker mean or lighter mean?
It means the receiving rate, because this guy is interested in ordered in terms of receiving rates. So pair 4, you have the highest receiving rate from, so therefore it's at the top of it. So we assign a credit to the costly pair. And each round, and we also have an expired bucket. So each round that goes by, we decrement that credit. So if in fact we're still sharing with this costly pair, we need to at least reduce the load on those costly links. So what happens then is that when the credit expires, we put it in the expired bucket, and we identify 2 local pairs, which will give us an equal receiving rate, and we expand our pair set to include those 2 local pairs. So effectively what we've done is we've replaced one costly pair with 2 localized pairs, which effectively gives us an equivalent download rate. So in effect, we're trying not to decrease performance for the user. Now, replacing 2 pairs with 1 and looking at download rates is actually a linear assignment problem, which we can solve in a variety of ways, like a bipartite matching, weighted. So we can solve this problem. So let's see where we are today. Today, yes?
What led to your selection of this particular algorithm? What spark? What idea? Or is this just an obvious random choice, or what?
Well, in fact, what we're trying to do is replace 1 pair with a certain download rate with 2 equivalent, with sum the download rate of the 2 pairs, the 2 localized pairs, 2 equivalent to 1 costly pair. So in effect, what we're trying to do is try to sum all the download rates of all the local pairs and find the total that we can use to replace 1 particular costly pair. So it's basically trying to look at, so we have, on one side we have local pairs, on the other side we have costly pairs, and we're trying to find a match in between them. So I think it kind of just popped up. I really can't. I think the problem really presented itself more so than it just happened because based on the problem set. I think more so the disjoint sets of costly pairs and local pairs and trying to find a match in between them.
So the disjointness is just partitioned into 2 groups,
yes.
Expensive or not.
Yes. And we're trying to find, can we use all the cheaper pairs to replace 1 expensive pair? So therefore we are looking at the different download rates, which we already calculate, and trying to just keep the same download rate overall. But yes.
What happens long term to expired pairs? Do they ever get reconsidered?
Yes, they do. Actually, what happens is that in the expired bucket, what happens is that every round that goes by, they build up credit, just like they lost credit when they were included. So after they have achieved that same threshold, like say 3 or 2, then they can be reconsidered. So we're not going to just totally eliminate them from the pair set. No.
So how do you identify the right credit to give to a peer?
That's a question, and that's where the heuristic thing comes out, and that's what we have to investigate. What is the right credit? And it might be the case that it might be dynamic, it might not be a static value. It might be, we have to investigate what is the exact credit to do. Because remember, our goal, it depends on, I think, on a lot of issues, that it might end up being a dynamic credit.
But wouldn't be a much simpler policy in which you just go to an outside your network peer whenever that particular chunk of the file does not reside within another peer within your ISP? Basically, you have 2 types of peers, local peers and non-local peers. Mm-hmm. And then you just select the best out of your local peers. If you run into any problem with your file, you go to the other set of peers.
Okay. I understand what you're saying, but I kind of skipped over some parts. The algorithm actually does a little more than that, the peer selection algorithm. And the reason for selecting maximizing download rate is because it's trying to achieve a type of fairness goal. Where in effect, what it's saying is that if you're not giving me, if I'm not receiving from you fast enough, I'm gonna drop you. Because I'm not only trying to maximize my download rate, I'm also trying to get rid of free riders. So you're assuming that I can simply select remote peers versus local peers. It doesn't really work like that. Because there's another goal in mind that the algorithm takes into consideration, which is download rate. So in effect, what I'm saying is that it won't share with remote peers unless the receiving rate is pretty high. And there are other mechanisms in place. And another thing to consider is that how is the peer aware of which is a remote peer and which is a local peer? It doesn't have any knowledge of that. And that's what AMP kind of gives it. Gives him knowledge of which peers are local or remote. So you see the two problems. One, we don't know what is a remote peer, what is a local peer from the perspective of the client. And two, it's not just selecting any peer. There's an algorithm in place to discourage free riding. So our current and future work. Currently, we're using the Intel ISP processor to develop and we're going to deploy it as an Open Network Lab plugin. We're actually working on that on a course. It's a project, so this is going on right now. And for the adaptable peer selection heuristic app, we intend to modify the BitTorrent client and then examine its performance with Anton O'Neill. Now, BitTorrent is written in Python, so it's not a massive code base like C or anything like that. So Python is a simple scripting language, which is not a significant investment in time. And our concluding remarks are, we hope to establish a mutually beneficial relationship between ISPs and P2P applications, improving network utilization and reducing, and at the same time, not degrading client performance. To do that, we propose Symbiotic P2P, which in effect informs BitTorrent of local peers and identifies peers on costly paths. And BitTorrent apps, in turn, adjust their peer selection algorithm to take into consideration feedback from the network. And we plan on actually implementing this in terms of a hardware device and an actual BitTorrent modification to the client. So I think Tom is not here, but it's going to be more than just a simulation. Tom. So thanks for listening, and any questions? Yes.
It seems to me that there's an issue with the ISPs having to sort of cache a whole bunch of MD5 hashes for the torrents, right? In order to make the comparison of two files are the same for two particular torrents, don't they have to have like some database of these things so they can figure out the
Well, you see a big database, but you have to understand that they only need to monitor active swarms. So it's not saying that they have to monitor every 2 million swarms. So yes, the hash is pretty small. I think it's a 128-bit hash. And one hash is pretty small in terms of, because the hash is not just a hash of the entire context of the file. But for now, let's just assume the hash is pretty unique. And what I'm saying is that it doesn't have to monitor every swarm. It selectively picks swarms that it needs to monitor. And in fact, it's not a huge storage of data because the hashes themselves are pretty small.
But isn't it difficult matching still? I mean, even if you're just looking at active swarms, tons of people are using BitTorrent. If you have lots and lots of active swarms, you need a lot of comparison.
I see your point, and you worry about the state that will be stored in the network. And I'm saying that it's not significant if you can see the other proposals. And in terms of other proposals, some proposals have actually proposed a cache where the ISPs would actively participate in the swarms, where they would set up their own BitTorrent client and help sharing. And I'm saying that there are ways of doing that matching using a little bit of state network, and we hope to propose a data structure to do that. But I'm saying it's a matter of just matching bits, so it's not as much state as you think, because you have to understand that the ISP is not concerned about every possible swarm going on. And some swarms, remember, it's only concerned about localizing its traffic. So I think somebody else has a question. Yeah. Go ahead.
Who's invested in having this work? Are the ISPs invested in having it work? Is BitTorrent invested in having it work? Are neither invested in having it work? And you're kind of proposing something to bring to the table. I mean, who's invested in this, and who would be easier to get on board?
Okay, well, first thing you have to understand that there is a case right now with the FCC, and last month it was filed. Basically, it's BitTorrent users complaining that, hey, you guys, we paid you for network access and you guys are throttling our traffic. So therefore, you're breaking an agreement. So this is going on today. Now the FCC is hopefully going to decide, is it legal for ISPs to traffic engineer? Or is it, so there's this debate going on. So as far as the ISPs are concerned,